On one of my recent trips to Japan, I went to Akihabara with my brother, who also contributes to this channel. You've probably seen his videos on electronics and bits and pieces. We found this power supply. It's a constant current, constant voltage power supply in one of the little sort of second-hand electronics parts shops. It was down in a basement, and we sort of came across it. There was the only one there, and as soon as I saw it, it caught my eye, and the price was negligible. So I was just like, you know, let's just grab it and have a look and see what it is. So it's a Sanden PET-07 CC power supply, and you can see the front there. It's got volts and amps as old analog needle style meters. Voltage range is 0 to 7 volt, and the amps are 0 to 10 amps. So a decent current there. Obviously the voltage is a little bit low, but I would assume that this being the 07, that refers to the voltage, and there's probably other power supplies in the same series, and they just had high voltage and lower current, so the watts were around about the same, and they could just adjust the circuitry to suit without having to re-architect the whole thing. I'm not going to go very far into this unit and the details and how it works and testing and things like that. I'm going to leave that up to my brother, who's going to do a separate video and show the internals of this thing. The reason I've got this here, and I've actually brought it back to Australia with me, and I'm going to send it back to him once I've finished, but I'll just open this little side plug-in board slot here, and you see it's just got 2 screws I've already removed. And if you have a look, by the way, I'll just quickly point out, you can see there's a big current shunt there. There's your big coil of wire, and you can see it's all through hole. But this board, we didn't know this at the time when we bought it, but we got it back and realized that it had an optional plug-in board. And it's just a slot style. I can just unplug that, just wiggle that a bit, and out it comes. And if you have a look at that, it's got a micro over here, very old school micro. It's got some other chips and bits and pieces. It's got a pin header up here with 4 pins on it. A couple of trim pots. See, it's sort of like looks like almost like it's a hand-drawn PCB. Bit of a bodge cap thrown in there. Bit of decoupling, I imagine. But this is actually, if you have a look on the back here and have a look at, if you can see that in the copper layer, it says RS-232 C. So this is an RS-232 or a serial communications plug-in board, an optional extra. So in today's video, I'm going to take a closer look at this and see if I'm able to get anything out of it. Sort of have a quick look at how it works, the architecture, which is quite old school. I think the date codes here are somewhere in the mid-80s, 86. There's one there. So that's probably what we're looking at. But yeah, we'll have a look at that. Obviously, we'll see what signals we're getting into the board and what signals we're coming out of the board. I'm assuming it's going to be this header up here. And see if it still works and if we're able to get comms out of it. The power supply itself does work. It's 110 volt, 100 volt Japanese voltage input, or same as US, I suppose, same plugs and everything. So I'll just be testing it with a step-down transformer. I've got a variac, so I can turn that right down to 100 volts, and then we can power this up and we can probe the header in here and see what we're getting into this board and have a look at that. So I think next thing I'll do is we'll take a closer look at the board and the chips, and we'll go from there. So I'm giving you a closer look here at this board. You can see the biggest piece of silicon that sticks out is this NEC D7810G chip here, and you can also see that it's quite a large chip, but the pins are spaced out in alternate sort of rows here, and that's so on these older chips, when things are all through hole, you could easily get more traces in and around the chip. It helped with layout, so that's why the older chips are sort of in that sort of pin configuration. I'll show you the data sheet that I found for this. You can see here it's a micro P, I'm assuming that means microprocessor, D7801. It's an 8-bit single chip NMOS microcomputer with analog to digital converter. So you can see a bit of the description there. Some of the stats: maximum frequency is 12 megahertz. Actually, a point on that, if you look at the board here, see they've got a 7.3728 megahertz crystal. And you think, why not go full 12 megahertz? Well, they probably didn't need that. But why choose such a strange frequency with this many decimal places? It seems a bit oddball. But the reason is because if you look at, because it's a serial board, if you look at the serial baud rates, say, I'm assuming this would be like 4800 or 4200 or 9800 or something like that, maybe even less. But you'll find that the crystal frequency divides very nicely into those baud rates, so that when you have your like digital bits, ones and zeros coming down the line, you can cycle this very nicely and get perfect timing between the bits and bytes, which leads to more accurate serial comms and less errors and those sort of things. And there is, if you look at the 232 and the 485, all those sort of specifications, they have the sort of tolerances that need to be adhered to. And usually the best way to do that is to choose a crystal that divides in very nicely with the baud rate that you're running at. And in this case, it happens to be 7.3728. In my own projects, I've used like a 14.7456 megahertz. Basically, I think it's just double that, and it works nicely for serial comms that are operating at the standard sort of baud rates. So this microcontroller or microprocessor has not a hell of a lot of ROM or RAM. It's got 44 I/O lines, which is fairly decent. It's got, yeah, all those sort of stats there that you can look at. It's not great by today's standards, but back then I'm sure it was a fairly decent microprocessor. So I mean that's a huge thing to note straight up, is that this plug-in board itself has its own microprocessing on board. It's like its own little computer module. It's not just like a straight out dumb 232 gateway or converter. It's not just taking the logic from somewhere else on the board. It's actually got the smarts and the brains to do that on this board itself, which is, that sort of changes the direction on how you'd reverse engineer something like this. But we'll continue on to this chip here. And this one, I'll just have a quick look there. It's a MBM2732A-30. So I've got the data sheet here. It's a Fujitsu part, and you can see it's a UV erasable 32K-bit read-only memory, and you can sort of see the pin assignment there and all those sort of things. So I mean that's obviously, as soon as you see like a silvered sort of sticker like that in the middle of a piece of silicon, you know that it's a window where you can then shine a UV light and erase the chip memory, and they put that on there to protect against erasure when you're not meaning to do that, because that would be disastrous, I suppose. So you can see also, if you have a look at the footprint, they've actually got 4 more pins, and if you have a look also down the edge, I don't even see that, but you see the silk screen. They've actually drawn like the 2 ends of the chips, and it's saying that if you wanted to option up, say, double the memory or a larger memory chip, you could just drop that straight in the board, and you populate this space here as well, and it would be capable of doing that. So a lot of older designs also did this, where they needed external memory like this. They would have the option to go up to a bigger memory if need be, and it can be on the same board, and you just drop a new chip. They just modify the BOM, and they can manufacture it with larger memory in there. So moving along, we've got this chip here, the NE5018, and the data sheet. It's a Signetics 8-bit microprocessor compatible digital to analog converter. So we've got a D to A converter here. Just having a look. 8-bit resolution. Positive supply voltage is maximum 18, and negative is maximum of negative 18. So we've got that chip, which is interesting. This here, digital analog converter. Perhaps we're producing an analog signal from our micro to do something or other over here. Next, up here, we've got a Mitsubishi, you see the little icon there. It's an M74 LS373P. And the data sheet here says it's an octal D-type transparent latches with 3-state outputs. 3-state high fan out output. Okay, semiconductor integrated circuit contains 8 D-type latch circuits. Okay. So you got data inputs and then your outputs. So it's a latch circuit, you got enable there. Interesting. So they're doing some sort of logic on this board as well, using like old school sort of signal logic like this. Interesting. We'll move on. I don't know what that means, but we'll just keep moving and we'll see what these other chips are. So we've got here is a TI part. It's an SN75188N. So here I've got the data sheet, and it's a quadruple line driver. And if you have a look here, it says meet or exceed the requirements of ANSI or EIA TIA 232-E. So straight up, this is our 232 line driver, is this chip here. And that being the case, I'm going to assume that this here, and being that the part number is 5188 and this is 5189, I'm assuming this is our receiver chip. We look at the data sheet. Quadruple line receivers. So we've got 4 232 transmitters here, and we've got 4 232 receiver lines here. This little thing up here is an OP-07 DP, and straight up that's going to be an op amp. Here's a data sheet, and you can see it's a low noise, single chip, monolithic fabrication, wide input voltage range, 0 to plus minus 14 volt, etc, etc. So we've got a little op amp there. So you can see that by looking at this, and we've also got two little trimmers here, the fact that we've got a microprocessor with analog to digital converter 8-bit inside, we've got a digital analog converter over here, we've got our 232 circuitries obviously here, but we've got an op amp as well, and we've got this sort of piece of logic here. Like straight up, this itself is its own little tiny board, its own little processor board. And because it's got this sort of analog to digital circuitry, I'm going to assume that there's no comms coming through on this pin header. I'm going to assume that the power supply is going to feed us analog reference voltages or signals that this board is then interpreting, reading, and then converting into our communications here, which is an interesting design. Obviously the power supply is quite old, it's all linear, and there's probably not a lot of smarts on the actual power supply itself. And then when they wanted to do the 232 interface, they were like, well, now we've got to have smarts, we've got to do some comms. So they ended up just putting everything on this board, and then I'm assuming that we're feeding through some references through the pin header here. This then reads those references and then communicates with the computer or whatever through this here. And actually with this little pin header, because I saw that was a Molex, a standard sort of 0.1 inch header, I went to Electronics, the computer store just down the road here, and I grabbed a little female socket for that. So I'll be able to create a little wire, a little loom, and then plug that into there, and from the other end of that I can then interrogate the RX-TX lines. So that's quite interesting. I guess this would have been quite expensive back in the day, but there it all is. So what I might do next is, because we're now sort of expecting to see some sort of analog signals through this header and not some digital comms or anything, what I might do is look back at the power supply and see whether we can bell out and see exactly what's going on this header, and then from there we'll look at the signals coming out of here and seeing if it's a lot of these boards, you just fire them up and they'll just be polling, they'll just be like outputting values and things. I don't know if that's the case with this board. Other boards you need to actually interrogate them, and if that's the case, it's going to be a lot trickier for me because there's no documentation on this at all. I can't find anything, so I may have to just sort of figure out the board rate and things and just start transmitting to this board and seeing what we get back. Yeah, but that's sort of the plan forward. So you can see, so I'm going to look at just belling out each of these little pins on this header here and seeing what sort of signals we're getting out of the power supply. And you can see this is the sort of plug that plugs into there. And by observing this board, I can already see some ground points that I expect to see here and things like that. So what I might do is just grab my fluke meter. You can see there's no real ground pour or anything, it's all sort of just individual traces, but there is a bit of a ground line going under here to each of these points, and it runs around the board. So if I get continuity between here and then pins on this line across here, which is the header, I can expect to see which pins are the ground points. So you can see here's the connector like that. So if I turn this over, we've got the top of the board along here and this is the bottom along here. Now I've got my fluke here set to continuity mode, so you can see that. So I'm expecting to see some continuity between these pins here being the ground, and I'm expecting these here. There you go, there's ground. So if we go from this being pin 1 to over here being pin whatever, I'll count them out. It's going to be 1 is ground, 2 is ground, 3 not, 5, 6, 7 and 8 are ground, 9, 10, 13 is ground, and 15 is ground. So it's 1, 2, 7, 8, 13 and 15. So that means the corresponding pins on the power supply plug itself here be 1, 2 and then 7, 8 I believe, and then 13, 15. They should all be grounds, and then from those points I can basically use that to help probe. So if I sort of plug that in there and hopefully get a contact, I might have to just wiggle this around a bit, but I should then be able to see what is going on these other pins. So it turns out I did have some difficulty getting my leads from my multimeter into this socket here. The leads just aren't quite sharp enough to make contact with these here, but because it's standard 0.1 inch spacing, I've just got a piece of this pin header and I'm going to just insert that into the socket now, like that, and that fits in there just nicely, and then that should allow me to probe just straight off those pin headers. So if I set my meter to continuity mode and we go for the ground pin 1 here, 2 should also be a ground, which it is, 3, okay, 3's showing a ground as well, 47 ohm on the meter, 5 is open, 6, 7, 8, 9, 10, these are all showing 0 ohm grounds, 11, 12 is open, sorry, 10, 11, 12, 47 ohm, 13, 0 ohm, 14 is open, 15 is open. So some of these are beeping out, but they've got some resistive, something in line there resistive, so that may just be part of the circuitry or something like that. What I'm going to do now is I know that these two here are going to be our ground, so I might just turn the power supply on and then run across with the multimeter in voltage mode, and we'll see what we get. So we're going to go from our ground to our other pin here. Careful not to short anything out. Getting 5 volts on pin 3. Negative 12 on pin 4. Positive 12 on pin 5. 0 on pin 6. 0 on pin 7. 0 on pin 8. 0 on pin 9. 0 on pin 10. 11. 4.3 on pin 12. 0 on pin 13. 11.6 on pin 14, and then 0 on pin 15. So I think what we've got is our 5 volt is our primary supply for our digital circuitry. We've got plus or minus 12 volts, which will be powering the op amp, and then I'm assuming that the voltages down this end, because they're a little bit off the 12 volt or those sort of things, I'm assuming that they're going to be related to our volt and current settings. So if I was to probe, let's just make an assumption here and go, what's this one? That one there? 4.3 volts. Okay. Now the voltage is currently set to just over 4 volts. So if I set that up to, say, around about 6 volts, I'm going to take a wild guess and assume that this is going to go up closer to 6 volts. There it is. So if I put the voltage up to, back down to, say, around about 2 volts. This is a bit rough, I'm just sort of swinging it over there. 2 volts. So I think it's safe to say that 15, 14, 13, 12 is our voltage reference, our output voltage reference. And our current is currently, well, there's no current being drawn at the moment, but what I'm going to do is turn the current up a bit. It was fairly far down. I'm going to turn it up a bit and see if that changes at all. 11.6, no. I think what we're going to have to do is draw some current out of this. I've got a DC load up here that I'm going to set up, and then we'll come back and we'll test pin 14 and just see that that does modulate with the current draw that this is measuring. The piece of equipment I'm going to use to load up the power supply for this testing is going to be this Manuo M9812. It's a 0 to 150 volt 300 watt DC load. It's way overkill for what we need, but it's quite convenient because it gives us a decent voltage current reading, and it has a remote 4-wire connection. So I'm using that right up to the terminals of the power supply so that it'll give us an accurate voltage and current reading, and I can ramp up the current load, and then we can measure on the power supply, on the pin header, what sort of reference we're getting out of that. So I'm going to show you just quickly the front panel of the power supply here. You can see the 4-wire setup. So these banana jacks here are actually what's loading up with the current, and these screwed into the terminals at the back here are the voltage sense. So we've got a voltage here, which is our 0 to 7 volt, and our current, which is 0 to 10 amp. And this is the adjustments, and the power switch is over here. Just quickly before we begin doing the testing on the pin out on the plug-in board, I thought I might just quickly put this power supply through its paces. You'll see here on the front panels what the voltage and current is reading, and we'll get a very accurate reading on the DC current load here. You'll see the voltage there and the current here, what it's set to. So straight away I'm going to turn on the power supply. You see we're reading 4.35 volts. Currently there's no load, it's switched off. But if I turn this knob down, you can see I'll turn it all the way down to 0. We'll see what the minimum is. So we're still getting just a little bit under 20 millivolt. So if we turn this up here until we read around about 2 volts, there it is. And now I'm going to load it up with 1 amp. So if I turn this on, you can see it's 1 amp load. And you probably saw on the front panel there the 1 amp come into play. So I can just turn this voltage up all the way up to 7 volts. I'll just creep it up there, I don't want to go too far over. So it's 7 volts there. You can see what it's reading on the analog display there. And what I might do is just put it back to 5 volts, just like a sort of mid-range sort of voltage, and then we'll ramp up the amps a bit. So that's about 5 volts there on the load, and you can see there on the analog current what it is. So now 1 amp. So if I go to 2 amps, you see our voltage has dropped a tiny bit. It's to be expected, I suppose. That's 4 amps. That's 5 amps. You see the voltage has dropped off. So I'm assuming now our current, you see the light, the constant current has kicked in. So if I turn this current back up, you should see we'll clear that out. So we're now delivering 6 amps. That's 7. There we go, we dropped off again. Constant current. So the constant current is actually working quite well. I'll just keep ramping that up. I'm just going to go full. Got 8 amps, 9 amps, and that's 10 amps at 5 volts, which it's doing quite happily. So if I turn this back down, you see that's where it kicks in there, and it drops the voltage off. So I guess one thing that we can test, if I just turn this right back down again to 0, I'll turn it off. We're at 5 volts. I want to see what the minimum constant current setting can be on this. So if I turn it all the way to 0, that's as far as it will go. I've set my load here to 0 amps. What I'm going to do is I go tens of milliamps. So if we switch on now, and we go 10 milliamp, 20, 30, 40, 50. Just going to keep clicking this up. So at 100 milliamps right now. We still haven't gone to the constant current on the power supply yet. Just keep clicking up until we hit the constant current. It's 200 milliamps. It's 250, and you can see that light's just come on there. 240, 230. You see it's sort of coming around there. So between about 200 milliamps and 250, you can see it kick in. If I wind up past that, you see it's still allowing, even though it says constant current there, I'm still out, the LED has come on this front panel, I'm still able to draw a fair bit. There we go. So 1 amp is basically, if we're just under an amp, so we're back into our full voltage. It's still regulating correctly. Even though the light came on the power supply, it's really only limiting 1 amp is the lowest it will go. So I guess it's old hardware, it's an old power supply. These days that wouldn't be acceptable. I mean, you'd need to be able to cut that out a lot lower than 1 amp, especially for doing digital circuitry, microcontrollers and things. You want to be able to wind that right back so you can protect your circuit when it's being powered and when you're testing with it. But I guess that's just a characteristic of this power supply, and that's important to know. So for this, I'm going to set my multimeter to the volts DC range again. What I'm going to do is I'm going to probe on the ground and on pin 14, which looks to be our current reference from the board into our plug-in module. So the first thing I'll do is I'm going to set the current mode all the way up to its max. I'm going to leave it at 5 volts, that's fine. And I'll just confirm that we're getting a 5 volt reading here as well. We're reading 5.022 on the DC load. 5.027, so that's very, very good. That's quite acceptable. Our current at the moment is reading 11.6. So there's obviously nothing being drawn at the moment. But yeah, we'll see. We'll just see how that reacts. So we're on. I'm now going to put 1 amp through this. There it is. So we're drawing 1 amp. You can see on the front. So now if I measure this again, 11.6. Still got our 5 volts. Just making sure there's not any other pins at it. There's a 12 volt rail, negative 12 volt, 5 volt. So it's got to be this pin here, 11.6. Okay, let's go 2 amps. 3 amps, let's go 3 amps. Still no change. What I might do is just force this into constant current mode. I'll turn the current setting down till that voltage drops off. Because it may just be an on-off thing, like it's in constant current mode or not. 11.2. Okay, we bring it back out of constant current mode. 11.6, so it's definitely changing with that. I wonder if I go to constant current mode, so it's in full-on constant current mode at the moment. I've turned the current knob all the way down. 11.2. Now I'm going to ramp up the current here to 5 amps. I mean, it's not doing that because it's powered off, but yeah. Just turn this up a little bit. Just back out of constant current mode again. 11.6. So if I go sort of halfway, so it's sort of starting to clamp a bit on the voltage. 11.22 the whole way. 11.22. So, I mean, all I can see here is that it's, let's just go up to full on 10 amps. There we go. All I can see is that it goes from 11.6 volts if it's not in constant current mode. There it is again. I'm at 10 amps now, and if I drop it into constant, like it's being clamped there, so the voltage is dropped off. 11.21, you know, same sort of thing. If I look at my voltage, 0.8, and that's right, I'm reading 0.8 on my DC load, so the voltage output makes a lot of sense. This current output, I'm assuming it's just like, it's not actually telling you how much current you're drawing and through this pin header, it's just saying whether you're in constant current mode or not. Maybe that's all it's doing, and it's just going 11.6 or 11.2, because I don't know. I mean, I can change the voltage, I guess. Let's go for 2.5 volts. I'll just confirm that here. It's 2.5 volts. 11.6, yep. So now we're going to clamp that. We're in constant current mode. 11.2. So that seems to be all it does. So it looks like we can read our voltage output through this pin header, and the only information that I'm able to get from the current is whether it's in constant current mode or not, and it's changing the voltage a tiny amount. Seems a bit weird. I mean, something could be faulty, I don't know. Maybe this is just normal, but I guess that's sort of what we're reading on the pins right now. So we'll continue with that. So now I sort of know what to expect on these pins and how it all goes through, how it's reading that, and from that we can try and reverse engineer this a little bit. I mean, we've got jumpers here, little switch jumpers. I've got no idea what they mean. I'm assuming this is a calibration for the voltage and current settings, and this would be our serial out, our 5 volt ground RxTX sort of thing. So just a quick recap of what I've measured on the pin out on this from pins 1 to 15. We've got pin 1 and 2 are ground. We've got our positive 5 volt rail, negative 12 and positive 12. The pins in the middle here, I'm reading 0 volts or just direct ground. I'm assuming that these will be for other plug-in boards perhaps. They're not being used in the case of this board though. We've then got our voltage reference on pin 12. We've got ground on 13, our current reference on pin 14, and then our ground on pin 15. So that's what we're looking at for this board. By the way, if anyone does know what, has any more details on this board, I mean, it says RS-232 CC. The only other reference is the RS-232 C marking on the back of this board here. If you have any information about this, or in fact the Sanden PET-07 meter itself, please let us know, link it in, comment below, because I've done a bit of Googling and I haven't found any reference to this power supply, the plug-in boards, or anything at all. It's just, there's just nothing out there. So hopefully I'm sort of starting some documentation of some of this old hardware for what it's worth. But yeah, if you do have any details, yeah, it'd be great to check that out.